And just a quick hello to everyone. We'll be starting the webinar in about a minute or two here as we get to the top of the hour.
All right, so it's about 10 a.m. now, so we might as well get started. I think we have enough people jumping in here. So we want to welcome you here from Control Station. I'm Mike, Director of Marketing. In today's webinar, we're talking about control valve essentials, sizing, turn down, and saturation. And we will be hearing today from our presenters, Damian Monroe and George Buckby. Damian is our EMA Integration Director at Control Station, and George Buckby is a consultant from Sage Feedback with a bunch of experience in the industry here. I'll give you a little deeper dive on Damian. Damian Monroe has nearly three decades of engineering and project management experience in process industries. As Vice President of Partnerships and General Manager of Control Station's EMEA operations, Damian is both a chief evangelist and he plays a key role in aligning our technologies with the needs of partners and practitioners. And similarly, George Buckby brings extensive experience in the automation and process industries. He is a PE and an ISA fellow. George previously served as General Manager of Expertune, which I'm sure some of you in the industry have heard of. And he's currently the president of Sage Feedback, LLC. And a little bit about Control Station, if you don't know who we are, what we do. We've been an active innovator since the 1980s. Today, we are proud to support an increasingly global clientele with 70 plus countries. We have installations in different plants, and our customers include leading manufacturers from across the process industries. So with that, we are going to dive into today's webinar, and I'll let George take it from here.
Great, thanks, Mike. Appreciate the introduction and welcome everyone. This will be an interesting webinar from a different perspective, I think, this time around. What we're going to be doing is talking about various aspects of valves that may be things that happen in the design phase, selections, choices that may be made in design phase, and how that winds up affecting how valves actually do control or facilitate the control of your process going forward. And then we'll dive a little deeper into some KPIs that can be used to monitor valves and look at some specific case studies using Plant ESP and tools to figure out what was going on with valve issues in specific plants. So we'll kind of walk you right through from basics to how it affects the control and then into some really specific examples. So looking forward to this today. If you do have questions, please either jot them down or type them in the chat area as we go along, and I think we'll have time at the end for some Q&A as well. So with that,
absolutely, George, get the guys to write them in at the start. You know, if you have a question, write it down, and we'll catch them all at the end. We won't be going through them as we go slide to slide, but we'll certainly circle back around and cover those questions at the end.
Great, thanks. So with that, let's go on to the start of the webinar here on the next slide. And we're going to start off with a little survey or a poll that should pop up on your screen in a minute, asking you how can control valves affect controller performance. And in this particular poll, select all that apply. So you can choose, one or more of these that apply. That first one, the word got cut off at the end, but it is making it harder to tune.
And the last one we're missing the VA from valves as well, I suppose.
Valves integrate control performance.
I'm sure you'll figure it out.
All right. Right. So we'll give this a moment. Mike, we'll need you to kind of clue us in when we're.
Yep. We've got about 50% answered.
Okay.
Now, so I'll wait till about 65% and we can close the poll.
Don't be afraid, everybody, just to put some tick boxes in there.
Yeah, I think we've got enough here that I can probably close it and we can take a look at some of the results here. Let me know if you can see the results on your side.
Not yet. Right, there we go.
There it is.
There it is, perfect. Yeah, okay, so a good spectrum across that, just to tell you now, there was no wrong answers, I suppose. The hint was in the check all that apply, and we see there's a spectrum across there, so we could say that it was a selection of it. How do they affect performance? All of those reasons, they think. Some things are front and center with us. It's an old plant. We see the last one, the controlled performance over time. They're the ones that need the maintenance. The ones up the top there, non-linearity. I suppose hot system doesn't have a non-linearity in it in some form. So they're certainly going to be. But understanding those is to where you can start to then make good decisions on it. George, you want to feed into those?
Yeah, I think you hit the nail on the head here. There are no wrong answers here because all of these things can happen because of control valve issues, either design time issues or mechanical issues that creep in over time. And so during the rest of the webinar, we'll be exploring how these different things can happen and how an issue with a control valve can make it harder to tune, introduce oscillations, limit your control actions, make small changes impossible, and degrade the performance over time. So we should be touching on each of those as we go along. And again, feel free to type in questions if you have them before the end. So great. Let's go on from here.
Okay.
Right, so we'll start with which factors about the control valve can affect or impact good control. And we've listed mostly some items here that, like I said, would be maybe things that were identified and selected for the control valve at design time. For example, the size of the valve, the valve characteristic, the flow characteristic for the valve, that is, as I open up the valve from 0 to 100, how does the flow change? Does it follow a nice straight line, or is there some kind of curve that goes with that? We'll talk a little bit about calibration issues. So when the valve is installed for the first time or bench set and calibrated, how that might affect control. We'll talk a little bit about positioners, whether positioners have some impact on control. And then, of course, deal with some of the mechanical issues that you may already have heard a little bit about, stiction and hysteresis and those kind of things. So we'll be hitting on these topics as we move along and looking at how that affects good control. So we can go to the next slide, please. So we're going to start with this topic of control valve sizing. When the plant was designed, when the process was designed, somebody had to make a decision about how big should this control valve be. And at that time, there are, of course, many different factors that play into choosing a control valve. For example, what are the design process conditions? What is the amount of production we're expecting from this plant? What's the maximum amount of flow we would ever expect to be needed through this valve? And then what's the lowest cost to achieve that? if you come up with, design conditions come up with, well, you need a 4.5-inch valve to meet the maximum flow rate. Well, it may not be a 4.5-inch valve on the shelf at your supplier. You go for the 6-inch valve because it needs to be bigger, big enough to handle the max flow, but you don't want to spend too much money on these valves. They start to get more expensive as they get bigger, and so on. So cost becomes a factor. And then, as you see on the right-hand side, there are many other factors that go into the selection of a valve. What type of process fluids? Is it corrosive, not corrosive? What kind of pressure is this valve going to be under? Do you need tight shutoff? What size line is it going to be plugged into? Is it going to be flanged? Is it going to be welded? All sorts of decisions, literally hundreds of decisions that go into selecting a control valve. Sizing being one of the most important ones. And you'll see in the next couple of slides how this plays out, that a valve of the wrong size can have a pretty significant impact on the control performance. So let's go ahead to the next. And we'll see in a lot of older plants, the process may have changed substantially since it was initially started up, designed, built, and started up. It's not uncommon to see a plant that's 20, 30 years old that's making completely different products at completely different rates than it was when the plant was started up. And
George, I've seen a few plants that radically change during startup, and that they've realized that they're running a different product, or they want to run a different product, and those changes can happen. Hopefully they happen later on in life, but they can actually happen quite early too, I suppose. Not everywhere, but I've seen plants that have, substantially changed from the time you turn it on to the time it's operating and stuff.
Absolutely.
So be aware of these from day one. I think feeding back off the last slide, it's the designers have done a really good job and have had a good estimation, guesstimation, and based on the available data. If the process is new, there's going to be gaps, and it's as practitioners, as commissioning, it falls to us to figure out where those changes have occurred, I suppose, and can we deal with them.
That's right. I mean, our designers, as you said, have a lot of experience, but nobody has a crystal ball about what exactly is going to happen when you start up this operation. So you may wind up in many cases with, if the process need has increased and you're now operating at a much higher flow rate than you initially planned on, that valve that you put in there from the beginning may turn out now to be too small. And if a valve is too small, it leads to this condition we refer to as saturation, which basically means the valve's 100% open, you can't go open anymore, right? That's it. And when it's too small, you're saturated, and the control really can't control to make anything increase in flow. All it can do at this point is allow you to make a decrease in flow rate. So at that point, really, if the control valve is too small, you almost might as well not have a control valve. You might as well just put an on-off valve there to allow it to shut, because it's not doing actually any control. The flip side of this, if the valve is too big, now that's quite an exaggeration there. This enormous butterfly
Great
valve.
picture.
It's a great picture, yeah. But you can see it would be very, very hard to make a small adjustment to flow with such a big valve. If you had this valve and somebody wanted you to make a 1 gallon per minute decrease in flow, you're just simply not going to be able to do that. Even moving that giant valve a tiny little bit, it's probably going to change the flow rate by tens or hundreds of gallons per minute. So it's really, the valve is too big, but it illustrates that point. And you do see that actually on a, maybe a less exaggerated scale in a plant. Even a valve that is 2-3 times bigger than it needs to be can make it very difficult to make precise control adjustments at lower flow rates. So this is how that plays out.
And again, there's regularly you'll see 2 valves, one in bypass on the other, so that you're trying to achieve both ends, particularly on processes that have a broad range of operation. You've got a small tweaking valve, I suppose we call it, in a larger, the heavy flows, you know, and that's not unusual to see, and I've seen it been adapted as a solution for these oversized systems to have this small bypassing system that will allow you to split the effort across them to tweak out, so you're not trying to do it on the really large valves.
Right.
Yes.
One last point here before we move on to the next slide is when the valve is too big, all of the mechanical issues associated with that valve are basically amplified, right? Because if you have just a little bit of stiction on this giant valve, you can see that's going to make a big pop in the flow rate, right? When it finally moves, or if you have hysteresis, or if you have any other mechanical issues around the valve, those little differences can make a bigger problem when it comes to controlling, just because everything is amplified by the size of that valve. So, okay, let's move on to the next slide here. And we'll talk a little bit about the valve characteristics. So the valve characteristic is the curve that tells us as the valve opens, you see that there on the x-axis of that chart, as the valve opens, how does the flow increase? For most valves, this is not a pure linear change, as you see in the red line in the center of the chart there, but actually it follows some other curve. This is called the inherent valve characteristic. And this is what you'll see published in the catalogs from the valve manufacturers and so on. And it relates to, and this is really important, it relates to the performance of that valve, assuming a constant pressure drop across the valve. Some actual installations are kind of like that. If you have a valve on the downside of a tank with a relatively constant level, you could kind of assume a constant pressure drop across that valve. That would be the actual in situ performance of the valve would match what is in the valve manufacturer's catalog. However, in most situations where you have some downstream back pressure coming from whatever else is downstream of that valve, other piping and elevation changes and turns and other valves and so on, the installed valve characteristic is actually a little different than what you see in the valve manufacturer's catalog, and that's because it's not a constant pressure drop across the valve, right? When the valve is open or closed, the pressure drop actually changes. So it's important to distinguish between those two things and to realize that even though I thought I may have purchased a linear globe valve with a nice straight valve characteristic, actually when I install this in my plant, it's actually going to look somewhat different than that. Okay.
It's going to drop those curves, George, isn't it? It's like, you know, as the back pressure comes on a system, those curves are going to get worse, like, you know, or they're going to affect the rate of change or the rate of flow. And you know, temperature is another one that has that same, you know, as equivalent to flow and back pressure, delta T on temperature is going to have a similar effect to valve effect, you know, is the smaller the delta T on your systems. Most systems have a good differential temperature on your process medium to your energies, to your steams, to your hot waters. But when those delta T's start to get closer together, it actually affects this as well. So it's something to be watchful.
So we'll touch on a couple of important points here that we can get from the characteristic valve curve, and that is the first one I'll refer to as turndown. Now, turndown generally means the ratio between the maximum amount of flow you would normally put through the valve and the minimum amount of flow you would normally put through the valve. So again, as the process was designed, as valves were selected, the person who selected that valve had to think about, well, normally we're going to operate at 500 gallons per minute, but maybe sometimes we're going to operate up at 800 gallons per minute and sometimes down at 200 gallons per minute because of whatever, different products being made, different production rates, different, whatever it happens to be. The difference, that ratio between the max flow and the min flow, is called the turndown or the turndown ratio. And that may be 2, 3, 4, 5, something like that with a single valve. When you get to larger turndowns, that's when people start to design maybe alternate systems, like a system with two valves, a small valve and a big valve, to be able to have good control, even though you have a wide range of flow characteristics. But turndown ratio is important because it tells us, what were people expecting in terms of where this valve is going to operate. And importantly, you'll see this point at the bottom here, effective process gain. When we look at how that valve is operating, how much flow increase do I get for each percentage of valve movement? You can see that if we have a very nonlinear valve characteristics, like this fast opening globe valve at the top, the green line, you can see that if I'm more than 50% open with that valve, 1% extra valve opening doesn't get me that much flow. So I have a very low process gain. Whereas if I'm down in the range of 10, 15, 20% open, a 1% change in valve opening gives me a very large increase in flow. So you can see how that plays out. If I had a fast opening globe valve with a high turndown ratio, that would imply that sometimes I'm going to be operating, at 20% open, and sometimes I'm going to be operating at 70 or 80% open, and that could create some real problems for tuning that we'll go into.
I think that's key, George, isn't it? In knowing where your valve is going to spend its life, spend its position, where the natural load of the system is, so that you're preparing to operate in those ranges, understanding that with the type of valve that you have, you need to set the process up to be respectful of them, I suppose, of the response, but also adherent of the capability, so that if in the bottom 10% of that fast opening valve you need to be probably more conservative, whereas in the 25-50% you have to be more aggressive to get your changes, I suppose.
Right, and with something as drastic as this one, this fast opening globe valve, it would be very hard to choose one set of tuning that would do well across that entire range. So, and
you're not going to get one,
right. We're gonna get into that a little bit in the coming slides. So we can move on from here to the next slide a bit. So a couple of things to think about here and how it affects tuning. Damien, maybe you want to take a crack at this.
Yes, absolutely. As I was saying, you've got the characteristic of your valve, but you've got your process fed into that then at the same time, and this installed characteristic of the valve is going to give you those profiles. But until you actually start to model across that range of process, you're not going to know where your response rate is. Remember, your process gain is that ratio of output change to PV response. So you want to be able to get that as accurate as possible as to where you operate, whether it's, valve position, which is going to drive the load requirement, or, the actual temperatures or flows that you want to maintain will give you the reverse of that. So understanding where you operate is going to be very key to getting correct function on it. That high turndown, operating across a very large range, it's going to be difficult. Is if you look at your fit distributions across the range of operation, you'll start to see where they're clustering, I suppose. The fits are clustering, and the function of the system, so the different process gains are going to be key to understanding that. Tuning conservatively, performance may suffer. If you try and make one size does not always fits all, is the thing. There's going to have to be a consideration for gain scheduling if you're going to if you expect that process to operate in any one of those curve plots. And I'd say the linear globe one is perhaps not quite a myth, but there's a lack of linearity even with that, with the process that feeds into it. So conservative tuning is going to make it try and fit everywhere, but it's not going to fit anywhere exactly, you know. So that's, you know, that good reckoner down the bottom, gain ratio of 3x or higher. If your ratio starts to change greater than 3 times, then gain scheduling is something that you should look at. You know, it's a very useful tool.
By gain
George?
scheduling, if some of you may not be familiar with that term, it basically means you would actually change the controller tuning programmatically so that when the valve was at a certain percent opening, you use one controller gain, and when it moved to a different opening, you would use a different controller gain. So this fast opening globe valve, for example, you might use one set of tuning from 0 to, let's say, 25 or 30% open, and then you'd use from 30% open on up, you would use a different controller gain, and that's called gain scheduling. It can be based on any number of things. In this case, it could be based on the flow rate, or it could be based on the valve position, but that can be done programmatically in your DCS to automatically change controller gains when you move into a different operating region.
Knowing your valve type and knowing the plots here is going to give you that decision or that information to say, we're going to need to gain schedule based on valve position. Now, once you gain schedule on valve position, you need to then confirm your operating points, I suppose, your operating ranges, and are they appropriate to it? Not that you want 2 sets of gain schedules, you know, one for valve and one for process. But again, if you know you're a fast opening valve, certainly you're going to benefit by a different approach in the 20% top and bottom, I suppose, you know, to get it into that control or to be able to react to it. But indeed.
Good.
We go next slide.
Now, of course, you know, we've talked a lot about these kind of design time issues or design time choices that may lead to issues later on with the valve. But there are also these mechanical issues that creep in with valves, sometimes right from the beginning, and sometimes they develop over time. So we'll talk about a few of these here. The first one, deadband, sometimes referred to as hysteresis. By the ISA definitions, they call it deadband, and they refer to hysteresis as being something a little more general than that. But basically what we're talking about here is deadband or looseness, mechanical looseness in the linkages around the valve itself. So if we try to tell the valve to open, if I have looseness, I have to tell it to open, and then finally it starts to move after it's cleared that range here, right? And then if I try to tell it to go back down, I have to clear that gap again before the valve actually starts moving down. So that can be, of course, a significant problem for control because you're expecting the valve to move when you tell it to move, and it might take several seconds for it to clear that deadband or that hysteresis, depending upon your controller tuning, the size of the valve, the size of that looseness, you know, those kind of things. That can create, again, essentially dead time in the control loop, which we all know dead time is really the enemy of good control. You have more dead time, you will have worse control. So deadband or hysteresis, as we often refer to it, can be a significant component there. Stiction is a slightly different term. Stiction refers to the resistance to the start of motion. So we tell the valve to move, it doesn't move, and then suddenly it pops and it moves. I often refer to this as like the refrigerator problem. You know, you're trying to position a refrigerator in your kitchen, and you put your shoulder against it and you try to move it, and it doesn't move, and finally you get it to move, but it moves 4 inches and you only wanted it to move 1 inch. So this kind of stiction, resistance to movement, and then it suddenly slips and moves, is what we refer to here when it comes to valves as valve stiction. And then lastly, I'll just mention this point that, you know, the zero offset, or in the valve calibration, making sure that we really understand how the valve was calibrated. I've seen many times where a valve was calibrated such that when the control output signal was maybe even 3, 4, 5%, the physical valve was actually fully closed. And sometimes people do this to kind of lull themselves into thinking I've got a really tight shutoff, then when I get to zero, it must be really closed. But you do see this problem happen a lot, and this can also cause some problems with control, particularly around startup, when you're trying to get things moving and try to get that valve open. And on the DCS screen, it says the valve is 5% open, but in fact, it's still physically closed.
And if the mechanicals of the valve sometimes feed into that as well, the valve needs to be 3-4% actually moved before it actually starts to open, expose an orifice, like open get the opening, because the sealing faces have to move that much to get them. So there can be some inherent zero offset in nearly every valve there is, but it can be exaggerated, as you say, by calibration, forcing that, the lack of movement in those. It'll close it down to zero, but it's not going to move it to open as it comes up. Indeed.
Right, and these three problems are not exclusive, right? You can have all three on one valve, and you can see that if a valve may even be sticky coming off of its seats. So that creates even another problem, another example of that. So you have zero offset and stiction to get that valve even to start moving or come open, and then when it does pop open, suddenly it's 5% open.
And if we think of our control system, and the PID is trying to integrate this error continuously, if we have lack of flow or lack of response, the PID is not going to know that. It's just going to go, I'm still in error, I'm integrating over time, and aggressive tuning will force that to start to oscillate. These mechanical issues start to show up in oscillation, which is something that you need to fully understand the cause of them, I suppose, so that you can address it. Because these lack of responses, the PID is a linear process. It presumes when you ask to move, it's going to. We know it doesn't, but this expectation on the calculation is, I'm getting response. Oh no, I'm not getting response. So I need to give more. And then we not only do we get that stiction effect, but we also get the wind up in the PID as well.
Right. So let's take a look on the next slide at how that plays out with valve movement and the effect on the process. So in the first one here on the left, you see the deadband issue, or what we had loosely referred to as hysteresis. If we have the valve in manual and we try to step the valve open, it opens, it goes open another step, and then we try to reverse direction. Deadband always plays out when you try to reverse direction. Remember, we've kind of pushed that valve open, and then we turn around and we have to get through that deadband before the valve actually starts going back the other direction. You can see how that plays out here. So not only does the process variable, let's assume it's a flow, take a while to turn around and get down, but also it comes down by a lesser amount for the same size movement in the valve. So this obviously has an impact on controller tuning from kind of two dimensions. One is that the effective process gain is changed because it didn't move as much as it did when you made a move here. And then also, it's a little hard to see on this chart, but also because it takes physical time for the valve to travel through that distance, that deadband, there's actually a small increase in dead time that can happen here. Now, this is even with the valve in manual. If the valve were in automatic and we had kind of a slow integrating movement here, the apparent deadband or dead time, I'm sorry, would be quite clear that there's an increase in dead time here. Now, let's move to the second one, stiction. Stiction is something that can, stop the valve from moving when you're trying to make small movements. So right in that first oval in the middle of the page, the first oval there, you can see there was a small change in control output made, but there was no corresponding change in flow. In other words, we told the valve to move, but it didn't move. Okay, and then we told it to move again, and suddenly it did move. In the flow did move. You can see the blue line started to drop down. And then we told it to move again, and nothing. in that second oval, you can see the control valve was told to move, but the flow didn't change. And then skip ahead to the third oval, and you can see it's kind of repeatable here that stiction is apparent. We're telling the valve to move, and nothing's happening.
It's a good a good check to if you want to measure the amount of stiction on your valve is set the loop to manual and just move very small percentage values, perhaps 0.2, 0.5% of the valve, depending on the size of the valve. The smaller the better, but step it in 0.2% amounts, and wait the dead time. If you know the dead time on your process, you have to wait that time to see does the response come in. If your dead time's as small as seconds, there's very little wait. But if you know your dead time on this process is 3 minutes, basically you have to wait those 3 minutes to see the response. But progressively making those 0.2% output changes, you'll get to a point where the process will kick and respond. And this, the cumulative of all those 0.2s is what will give you the amount of stiction you have on that valve. It's a useful way just to understand how big a stiction issue you have, I suppose.
Yeah, to quantify it so you can make a decision about whether you're going to take the time to do some mechanical repair work around that valve. The last chart on this page is showing you the stick-slip cycle. That's a mouthful, a stick-slip cycle. Basically what this is, when that valve, when that loop is in automatic with a sticky valve and some integral action on the controller, which most controllers have anyway, this is the pattern that you'll see happening. The control output will move in a sawtooth pattern. We call that a sawtooth pattern, like a triangular wave. That's basically the integral action saying, give me a little more, give me a little more, give me a little more. Oop, valve move, give me a little less, give me a little less, give me a little less. That's the integral action on the controller operating. And then you see the impact of that on the process variable with the stiction involved. You know, the valve does nothing, and then suddenly it pops to a new position. And once it pops to a new position, then the control output starts going the other direction, and then it takes a while, and then suddenly the valve pops again and the flow increases again. And so the PV, or process variable, looks like a square wave, or sometimes it'll look like, I call it a shark fin, okay? But it can be a square wave or a shark fin pattern, and the control output in this triangular pattern. So this is a kind of a telltale sign that you have stiction on a valve, and it's a good way to diagnose the issue and be able to pinpoint it so that you're not thinking, oh, my loop is oscillating, I must have a tuning issue. No, this is a valve issue.
Yeah, I was going to say that the tuning, aggressive tuning, is going to show nice sinusoidal curves in the PV values. You know, they're not going to have those straight, rapid changes. So if you start to see these straight, rapid changes, it's a stiction consideration that it is. So just a general comment on stiction. You know, quantifying the amount of stiction will drive your decision on, well, what am I going to do about it? You know, if you have 1% stiction, you've lost 1% of your range of control. You know, so that's fine if your instrument is a 0 to 1,000 millibars. You've only lost 1% of that. But if your instrument is and you're controlling across a 0 to 50 degrees of temperature, you've lost, you know, a half a degree of temperature on that system. You know, so that you're, and if you've got, well, I've only got 3% stiction. Well, then you can have, you may have a requirement on your system to have quite tight control, and somewhere around 3%, you're going to lose that. You know, as I said, you know, we see systems that can have significant numbers of stiction on it. You know, and you know the presumption is it's only 3%, but you've lost 3% of your range of your process controllability.
If your valve is operating at 15% open and you have 3% stiction, that means you're only going between 12 and 15. I mean, that can be a huge range, you know, huge
Yes.
change in flow when the valve does finally pop and move. So, great. Let's move on to the next slide here.
Okay, another survey.
Right. Yeah. So in this survey, we're going to ask, who has the responsibility in your plant for control valve performance? notice I don't say control valve maintenance. I'm saying who's responsible for looking at the performance of the control valves. This time you only get to pick one.
Kind of a loaded question, I suppose, but just, you're going to focus on your own area of responsibility and go, yeah, it's not me, or oh yeah, it is me, but it's how we doing, Mike, on the pickups? Again, click something. There's no wrong answers. Well, technically, but
We're just pushing 65%, so I'll close the.
okay.
Great.
Excellent. Yes, so, and George, I'll let you lead off on this one.
Yeah, I mean, I think this is one of those that I'm not surprised at all. It's very typical that nobody kind of knows whose responsibility the performance is. Maybe it's left to the control engineers, but it's something of a mechanical issue. Maintenance may or may not even be aware of, the impact of these things on control and on the process, and kind of see a valve as a mechanical device with mechanical issues, and yeah, I can tweak it up, but does it make any difference if I tighten down on the packing too much or not? Does it make any difference if these linkages have a little bit of play in them? So it's not always clear, the relationship between the mechanical issues and the performance issues in the plant. So it's quite interesting to see this spread. And I think in many cases, it's often overlooked to say who actually has that responsibility.
Again, it sometimes it seems to come back to different organizations have different ownership on systems. The control engineer classically is a programmer. He doesn't operate the plant, and it regularly falls on the control engineer to understand, justify, explain why the control system's not why the PID valve and instrument are not doing their jobs. And I'm not surprised that the percentage in control engineers, there is an expectation here, but a lot of sites, a lot of installations, a lot of industries, the control engineer is just a programmer. He's not really an operationals person. I would nearly the responsibility. Operations or process is where it should be, because it's their responsibility to have a good valve that is doing what they want it to do, is the thing. So it's an operations focus that will pull in the other areas. There's almost like everybody has a responsibility to this, but it is very much a performance, process, and operations role.
I would say also, Damien, it's an evolving topic in that 10 years ago or more, maybe nobody would even know what we're talking about by saying the valve performance. Nobody even measuring it on an ongoing basis, or knowing what's a good number or a bad number. What's a good amount of stiction or a bad amount of stiction,
Yeah.
or a good amount of hysteresis. What's normal. Those things were not really as widely known and practiced. But these days, there's more and more emphasis on good type performance, more and more requirements for your process to do better. And so things like valve performance are starting to creep up onto people's radar. And in doing so, then management starts to assign responsibility for somebody to look after that.
I think it's a nice feed into the next slide there. If you can measure it, you can control it. And I think that's what's happened over the last 10 years, that there's more understanding of the data that's coming back, more accessibility to that data, I suppose. So we can go on to the next slide there. So with this here is just, let's look at a few of those of the things we talked about, and how do we measure them, and how do we do something about them? The first two, stiction amount and stiction likelihood. if we were in a room and I put a show of hands as how many sites have you are represented here that have feedback on every valve that they have on site? There is no site that does feedback on every valve, so you don't know that the valve is not where it's supposed to be. You have to sort of make statistical analysis on it, and that stiction amount and stiction likelihood are the two ways that you can look for it. Remember, we described what stiction is. It's that sawtooth relationship, that slow PV change and then a rapid response, and then a slow PV and then a rapid response in the other direction. Statistical analysis of that process data relative to the output gives you information, gives the data analytics people the ability to go, that has a likelihood of stiction because it is exhibiting stiction characteristics, I suppose. By calculating that, you don't need to have valve feedback. You just have to look over time as to what the relationship between output and PV is, and it gives you this very strong relationship. The likelihood and the amount statistically, you know, there's 60% likelihood of a 4% stiction. You know, it's giving you that statistical mark. It's still 40% wrong, I suppose, you know, from a likelihood, but it's showing you these likelihoods and these amounts. Again, we're just working on numbers to do it, but it is quite firm, and we'll see that in a case study in a minute. Output in upper and lower region, you know, that there's two problems here. The lack of ability, if we think back to our valve plots, the lack of ability to affect a significant change in those lower and upper ranges of the valve movement are going to cause you problems. Whenever I'm standing in front of a problematic valve and I go, why am I here? I'm looking at these things. Is the valve living in a very restricted range? Is it in the upper or lower ranges? So it's barely started to flow, or it's barely got anything left to flow. It's maxed out, or it's actually fully closed out and it still can't cool enough. You know, sizing is going to be a key there to it. Again, one of my cautions or red flags is valves that live in the extremes, I suppose. Mechanical health is something that, you know, is going to feed into valve maintenance, calibration, instrument feedback into that. You know, back to our earlier questions about who's responsible. You know, it's to have a good functioning valve, we need to have good instrument information. We need to have a good tuning on our control system. If one of those is out of balance, then mechanical health is going to go down quickly. Every single valve out there coming from the vendor will say this valve is guaranteed for X cycles. Now it could be 1,000,000 cycles, and we're never going to reach that number, you know, but you can reach that number quite quickly if you have oscillation, if you have stiction, because you're constantly changing the valve. You know, percentage time at limits, there's the other one that is going to give you, we're maxed out. You're not in control if you're at 0% or 100%. So if there's a sizing problem in that can feed into it. Now, this kind of metrics doesn't come from your control system. Your control system doesn't care about performance. It cares about controlling. It's going to look at the operation of the process. It's going to have all the data where you're going to start monitoring performance, but it's not necessarily, it's going to tell you when you have a problem, when you an alarm, when you trip a high level, but then the problems are underlying in it. Model distribution, we talked about that already, about this. Where does your model fits live? Where do you normally operate? The way I describe this is, if you control a process at 2 or 3 different set points, you should have 2 or 3 different model fit considerations for it to accurately control. One size won't fit all necessarily. You know, you may find an average that will work okay in the 3, but you know, you may need to work on it. The analytics are going to do that for you. I have a case study, next slide please, that will show us the effect of this. One sec, now my slides is just a little funny. So on this case study, we see a plot there of an oscillating loop. You're looking at a red set point in the middle of the upper trend with the green PV around it and the yellow output below it. This was a loop that detected stiction on, you know, but if you look at that process there, it's oscillating, you know, so, well, oh, that's a tuning problem, you know, but it's to dig deeper into that data. In automatic, the oscillation and the speed of change can cause that fluctuation just to constantly work, but it's only when you start to look into the data, and you can kind of see it in the lower phases of oscillation between those two large rapid oscillations. You're starting to see the sawtooth on the tops of those plots, but again, it's very difficult to see this just by observation of a trend over whatever time period we have there. Really, it's where this information starts to feed into is when you start to statistically analyze the response. And if we go to the next slide, this actual customer was saying that there was an oscillation on the process, and it was only when we started to dig into it with stiction did we show that the effect was was a stiction effect, and it was 5% stiction on this valve. You know, it's a significant amount of stiction. You know, the likelihood is a super strong number, 83% likelihood. So every time the valve moved, we were seeing 83% of the times when the valve was moving, we were seeing a stiction type effect on it, you know. So this kind of, these focused metrics will give you that information to actually build into it. And next case
That's a really
study
good
now.
point, Damien.
Sorry,
I think
George,
that,
go ahead. Yeah.
no, that, you know, you may have hundreds or even thousands of controllers and control valves in your plant. And most plants don't have the luxury of having somebody that can scan through and look at every oscillation and every valve every day. You just don't have the personnel and the time to do that. And this is why using KPIs and loop monitoring is so important, because it can draw your attention to that one problem out of the hundreds of, yeah, okay, there may be hundreds of things happening in your plant. This one is pretty clear to say, hey, here is a valve that absolutely needs some focus and some attention, and fixing this problem will help to stabilize the operation.
In reality, that stiction started at 1%. X period of time below. It's monitoring it from back then, is then go, okay, we're not too concerned about 1%, but if that goes to 3%, we're going to do something about it, or we need to do something. We have a shutdown coming. You can feed this type of data into that to allow you to do it. But indeed, you don't care about the 1,000 loops that you have on your plant. You only care about the top 50 worst performers. They're the ones that you start to track and start to use. Just go to the next slide there, please. This one is you know, tracking your valve positions at max and min positions give you the information to start feeding into the other considerations with why are we performing poorly on this process? Why is my average absolute error high? Well, if you're up in that top range or maxed out during times, it's going to give you those values that are going to start to well, I cannot heat or cool the system anymore because I'm maxed out on it. You can see there was over on the left-hand side, there was a period of time where it was in normal operation and has just started to drift up. Can be because of extra load on your plant. It could be because of scaling in a heat exchanger. There could be a condition that's forcing the system to try and work harder. As part of my why am I here questions, I always go back through the trends to look for history of when did this problem start to occur. And we can quite clearly see at the start of this period, there was a normal operating a mode on it. But the output distribution, you can see this on trend, but when you connect it using analytics and loop monitoring to other conditions, average absolute error going out, you're starting to drift as we go to full scale or min scale is what it is. This one here was if you just go to next slide. We can see that it just the metric was spending its time at the limits, I suppose, you know, and that's, you know, even if it's normally spending that time, if we know our valve profile and we know this valve is living in the 85-90%, we're going to know we're going to have to adapt our control for here to because of the profile of the valve. George, any feeds on that, experience with like
I would just
valves
say
that are
when you
maxed?
have this kind of situation when when the valve is fully open all the time, you have no control. Imagine driving your car with the accelerator pedal all the way to the floor all the time. You don't have control. You don't have any control over the speed. Here you don't have any control over the process. So this is a real red flag when you have a valve that's operating at one end or the other all the time. It really tells you, hey, you've got maybe a big process problem, but definitely a problem with being able to control with that loop. And you see this all the time in different industries and different areas of the plant. Dilution valves are another one that's typically, you might see it at 0% all the time, meaning that the process is already dilute enough, I don't need to add any more water or whatever it is I'm putting in there. So you see it at the other end of the scale when the process is a little bit off. Or you see it here with the valve 100% open when maybe the valve was just too small. Maybe it's time to put in a bigger valve or to remove some restrictions from the line or change the trim on the valve or do something. But when you're at 100% or 0%, you really essentially have no control.
Yeah, the other useful function of this is we're planning to do a process increase next year. Will the plant take it? Very quickly, you can look at your output distributions on your critical processes and see, well, these are all maxed out in this particular unit, in this particular sector of your plant. They seem to be fully loaded anyway. We're not going to be able to do a 20% increase in throughput next year unless we make plans for it. So it feeds, loop monitoring is going to feed into lots of different areas of responsibility, not solely just operations and function on it. Next slide there, please. We're conscious of time, we have about 5 minutes. So last question there, just to quickly, this is the one just to give us the opportunity to hear from you on, your interests, your is something piqued your interest here that you want to find out more? Our tools, our expertise feed into all of that, and you've just seen a very small smattering. Hopefully you've got a few tips and tricks out of it, on how to accurately detect. But as I said, just feel free to. And the last one is okay as well if that's your choice. But as I said, we don't mind so long as you answer one of them, I suppose.
Right, and again, choose all that apply. So.
Yeah, that's fair too. Yeah, we have a great training class, practical process control that can give you, 4 half days of process understanding and then how to apply the PID tuning approach to that. Mike, how are we doing on coverage?
About 60%. We'll just give it
okay.
Good, and now's a good time to start typing your questions. If you have questions.
I was just going to say it, George. Yes, okay.
Yeah. If you have any questions, type them in, and we'll be happy to take a few minutes and answer them.
We're running short on time.
Right.
Okay, we can step forward. That future webinars, that's great. Training opportunities. Look, as I said, the practical process control class. Look it up. It's a great class. Just the contents in it are brilliant.
Right.
Questions, I suppose. Mike, have we any questions coming in?
We have a couple. I will hide the results here and dive into that. So one of the questions asked was, which of these issues apply to dampers as well as valves?
Yeah, I'll take that one. Most of them. Dampers can be undersized, they can be oversized. Dampers are notoriously nonlinear in terms of their performance. So we talk about that characteristic curve. It's going to be quite different. Usually when the damper opens up just a little bit, you start to get a lot of flow, and then as the damper is reaching 60-70% open, the curve is very flat, so you don't get much out of it anymore. So you have those sizing issues, you have the nonlinearity issues. mechanical issues, oh my gosh, yeah, linkages and stiction and hysteresis run rampant in dampers, because usually you have not just kind of one stem to move, but many individual louvers on the damper, and each one kind of have its own stiction and binding, or hysteresis, looseness, and deadband. So very much so, all of these play out on dampers.
The problems get worse in dampers, I suppose. You know, at least in a valve, there's one mechanical device that's opening and closing, but in dampers there can be multiples that are going to. If you want very accurate control, damper shouldn't be your first choice, I suppose, is what I'd say.
And for the interest of time, maybe we'll take one other question, but what is the biggest cause of stiction?
I'll go with this one, George. You know, so let's think about what stiction is. It's overworking the valve. The valve has been stroked so many times, it's running into its million cycles. Now, what's going to cause that? What's caused the overworking? I would argue aggressive tuning. I've yet to come to a loop. Okay, so it's that I'm not, but I've yet to come to a loop that I found that it needed to be as aggressively tuned as it was. There's always going to be a consideration. There should be a consideration to tune just enough. Because when you tune today at an aggressive tuning and it's reacting very quickly and it's moving, first of all, you're losing stability, but do you need to be that aggressive? Over aggressive tuning is the answer to that stiction question, I suppose. But it's a problem that we tend to push down the road as tuners, because we tune as quick as possible to get the reaction we want. But a million cycles later, if that's 6 months or 18 months, is going to start feeding back into it. You can argue that maintenance will, you know, if they're doing their jobs, they'll keep them, but that's not always possible with, you know, continuous run plants, etc. So soften, be as conservative as you can be for your tuning. Now,
the other thing I would add, Damien, if you would, is because there has been continued environmental pressure on plants to try to reduce emissions, and particularly fugitive emissions, more and more plants have really been cracking down on emissions at the valve stem, and therefore tightening up on the packing at the valve stem. And of course, that's great in terms of reducing the fugitive emissions leaking out, but also what it does is it puts pressure on that valve, so that you need more and more torque to move the valve. You know, whether it's a rotary valve or a linear stem valve, you have this problem. It gets harder and harder to move the valve the tighter you make the packing. So that's also a contributing force to more and more stiction these days.
Yeah, indeed. Just to close out on the tuning, if gain scheduling is the least used control philosophy that's put into process, and it can be the most effective, because if you can change your tunings from where you operate, you'll then be fast when you need to be fast, and you'll be slow when you need to be slow, and it allows that to use the valve efficiently, effectively, and minimize those opportunities. We're going way over time at this stage, George, so I think we'll
hand it back to Mike here.
Indeed. Thank you for your time. It was great attendance on that one. Hopefully you've learned something. You have our contact details. You can see our sales leads there. Please feel free to reach out if you've got further questions, or if you've got you want to clarify something, or you're interested in our products. Absolutely reach out to us, and we'll, as your answers to the previous questionnaire, we will certainly reach out to those. But any of those none of the above people, I'd like to know where you are with it. I suppose is there an opportunity to explore further? Mike, handing back over to you. Thanks.
All right, great. Thank you, everybody. Appreciate the attendance here. And, you know, a lot of the answers were future webinars, and we do have a webinar planned every month coming up for 2025, and that will be posted on our website and also via email marketing. So keep an eye out there and check back to stay on top of that. And we appreciate you attending today. Thank you very much.
Thanks,
Thanks very much.
everyone.
Bye-bye.